Welcome to the deep dive. Today, we're looking beyond just what artificial intelligence does
Right, we're digging into how it actually tries to think.
and, where those different approaches even come from philosophically.
Yeah, we're diving into the main ways people classify AI systems.
We'll be unpacking the core paradigms, symbolic AI, connectionist models,
Mm-hmm.
like neural networks, and hybrid systems, too.
Exactly. We're drawing on some great research here, including work by Gerardo Iovan and Giovanni Iovan, to really understand their strengths, their, well, fundamental limits.
How things are evolving now.
And you'll see it's fascinating how each type of AI really reflects a specific philosophical view on what intelligence is.
It really does. It mirrors that whole historical shift, doesn't it? From purely rationalist logic to more empirical, experience-based ideas about knowledge.
Precisely. Understanding this, well, it's kind of a shortcut.
A shortcut, how so?
Well, it helps you quickly grasp why a certain AI might be amazing at one thing.
And then completely fall apart when the situation changes slightly.
Exactly. Okay,
Yeah.
so let's start at the beginning. The real OG of AI, symbolic AI, back in the 50s.
Right, the rationalist approach, capital R.
Totally. Based on pure reason, structure, formal logic.
When people first imagined thinking machines, this is what they pictured, right?
Right.
Something super logical, following rules, almost like Aristotle building a computer.
That's a great way to put it. Symbolic AI really is about intelligence coming from syntax.
The syntax,
Meaning the formal manipulation of symbols, letters, numbers, concepts represented as symbols according to very explicit, pre-programmed rules.
So you give it a big database of facts and a set of if-then rules.
And its thinking is just applying those rules to deduce new facts, like solving a logic puzzle.
And there was that big idea behind it, the physical symbol, something.
The physical symbol systems hypothesis, Newell and Simon.
Right. Sounds heavy, but what did it basically say? Why was it such a big deal?
Well, it was radical because it proposed that any system, a computer, maybe even something else entirely, if it could just manipulate physical symbols according to rules.
It could achieve genuine intelligence.
That was the claim. Intelligence as pure computation, separate from biology or embodiment or anything physical.
Wow. So the hope was just write enough rules, get enough processing power, and bam, consciousness.
Kind of, yeah. That was the dream for a long time. And look, for certain tasks, it's great.
Like what? Chess, math proofs.
Exactly. Things where the rules are fixed, clear, explicit. Symbolic AI can crunch through those huge knowledge bases, reasoning logically, way faster than we can.
There's always but.
Always. The big problem is that it relies on those static, explicit rules, the real world. It's not like that.
It's messy, ambiguous. Context changes everything.
Precisely. If the input doesn't perfectly match a rule it already knows, the system just breaks. It can't cope. It's too rigid, too brittle.
Okay, so that approach hits a wall. If you can't possibly write down all the rules for navigating the real world, what's next?
You look at the one system we know navigates the real world pretty well.
The brain.
Exactly. Which leads us to the sort of opposing philosophy, connectionism.
And this lines up with empiricism.
Right. The idea that knowledge isn't innate rules, it comes from experience, from sensory input, from learning.
So instead of programming rules, you try to copy the brain's structure.
Kind of. You build these artificial neural networks, lots of simple little computing units like neurons.
They're connected together.
Yep, connected together. And the knowledge isn't in explicit rules, it's in the strength of those connections, the weights between the units.
So it learns by adjusting those connections based on data.
Exactly. You show it tons of examples, millions of cat pictures, say.
And it tweaks the connection strengths, the weights.
Until it figures out the patterns that mean cat. It learns to generalize from the data it sees. Signals pass through, weights get adjusted. Simple concept, but powerful.
The whole thing hinges on the data then. Lots of it, and hopefully good quality data.
Absolutely. It directly reflects that empiricist view. Experience shapes knowledge.
It sounds incredibly powerful. But how do we know it's really understanding anything? Or is it just getting really, really good at pattern matching? Does it run into its own philosophical problems?
Oh, definitely. That's a huge question, and it brings us right to the major challenges, the limitations of both these big paradigms.
Okay, let's unpack those. Where do we start? Back with symbolic AI.
Let's. The big one for symbolic AI, its real Achilles heel, is something called symbol grounding.
Symbol grounding, okay? Where the symbolic system can shuffle the letters CAT around perfectly based on rules.
But it doesn't know what a cat is.
Right. So grounding is about connecting the symbol to the real thing.
Precisely. It's this fundamental problem: how does a symbol inside the machine get linked to what it actually refers to out in the world?
Can you give an analogy?
Sure. Imagine trying to learn Chinese using only a Chinese dictionary. You look up a word.
And the definition uses other Chinese words you don't know.
Exactly. You can learn all the rules of how the symbols relate to each other, but you never connect them to the actual sounds or objects or feelings they represent. You're stuck in a loop of symbols.
You can manipulate the system perfectly, but there's no actual understanding of the world outside the dictionary.
That's symbol grounding in a nutshell. Without that connection to real-world experience, the symbols are just uninterpreted tokens. It's the flaw baked into that pure, rationalist, rule-based approach.
Okay, I get that. Now, flip side, connectionist systems, neural nets, they are connected to sensory data, right? So they avoid that specific problem.
Largely, yes. They learn from the data that comes from the world, but their success creates a whole different headache: the black box problem.
Ah, the black box. I've heard this term a lot. What does it mean in this context?
It means that while these networks can be incredibly powerful, especially modern ones with millions or billions of connections.
The weights we talked about.
Right. The learning is distributed across all those tiny adjustments. Data goes in, a decision comes out. But figuring out how the network actually reached that decision, the steps it took, it's incredibly difficult, sometimes impossible.
It's opaque. You can't easily trace the reasoning.
Exactly. You know, it decided that medical scan shows a tumor or that the car should brake.
But you don't know why. Was it the key feature you expect? Or some weird artifact in the data it picked up on? Some subtle correlation?
And that lack of transparency, that opaqueness, is a massive issue for anything safety critical: medicine, driving, finance.
If it makes a mistake, you can't really debug it easily because there's no clear logic trail to follow.
Precisely. The reasoning, if you can call it that, is smeared across millions of tiny weights. It's just too distributed and abstract.
And imagine this black box thing gets even worse as the networks get more complex, like with deep learning.
Exponentially worse. Deep learning is really a subtype of connectionism.
Defined by lots of layers.
Yeah, multiple hidden layers of those neuron-like units between the input and output. That depth lets them learn really complex hierarchical patterns from raw data automatically.
Things like understanding images or natural language, or playing complex games like Go.
Right. They can achieve superhuman performance on very specific high-dimensional tasks, finding patterns in massive data sets that humans would just miss.
But they still have the black box problem.
Oh, absolutely. Often even more so because of the complexity, and they don't fully escape philosophical issues either. Some argue they still have a form of grounding problem, just different. Plus, they bring in a very practical issue called overfitting.
Overfitting. Okay, what's that about?
Overfitting happens when the system learns the training data too well.
Too well? How can it learn too well?
It starts memorizing not just the important patterns, what makes a cat, but also the random noise, the irrelevant quirks, the specific examples in that particular data set.
Ah, so it gets perfectly tuned to the training examples.
But then it fails when it sees new data from the real world that's even slightly different.
Like if all the training cats were black, it might struggle to recognize a white cat. Or, like your earlier example, if they were all on blue couches.
Exactly that kind of thing. It learned cat, thing on blue couch, instead of just cat. It hasn't generalized properly.
So it becomes brittle again, just in a different way than symbolic AI.
Right. And because these models train on such massive data sets, they can also slip up and amplify any biases present in that data, societal biases reflected in text, or skewed image selections. They become hyper-tuned to a potentially flawed view of the world.
Okay, so we've got symbolic AI, rule-based, logical, but brittle and struggles with grounding.
Yeah.
And connectionist AI learns from data, powerful, but opaque, and prone to overfitting and bias.
Check. Seems like we need something that combines the best of both.
That feels like the logical next step. Which brings us to hybrid AI. This is where it gets really interesting, trying to merge that Aristotelian logic with brain-like learning.
It's the big challenge, really. Hybrid systems try to integrate elements from both sides. You get the explicit reasoning power of symbols
with the learning and generalization ability of neural networks.
The goal is to overcome the weaknesses of each one alone. But it requires getting these two very different ways of representing information to talk to each other.
How does that work in practice? I know our sources mention specific architectures like CLARION. from Ron's son.
Yeah, CLARION's a good example. It's designed with distinct parts. You have explicit high-level components using rules, that's the symbolic bit.
Okay.
And then you have implicit lower-level subsystems, often neural nets handling things like perception or motor skills, the connectionist bit.
So let's take a robot example again. Navigating a room.
Okay. The connectionist part may be a neural net, processes the raw camera feed. It sees shapes, textures, identifies obstacles, implicit knowledge.
Got it. Just pattern recognition from pixels.
Right. But the symbolic part holds the high-level stuff. My goal is to reach the door. A large rectangle is probably a wall. The map says the door is over there. Explicit rules and knowledge.
So how do they connect? The low-level vision needs to inform the high-level plan.
That's the key, knowledge transfer. The vision system might output a symbol like obstacle detected at XY.
Okay.
That symbol gets passed up to the symbolic reasoning layer. That layer then uses its rules. If obstacle detected and goal is forward, then calculate new path.
Ah, so the connectionist part provides the grounded perception, and the symbolic part does the logical planning based on that perception.
Exactly. And information can flow the other way, too. The symbolic planner might tell a connectionist motor control how to move. They learn from each other, refine each other. It allows for a much richer, more human-like interaction with the world.
That makes a ton of sense. You get both the seeing and the reasoning.
It's definitely powerful. But here's the hybrid challenge.
Another challenge.
Of course. Building that bridge, that knowledge transfer mechanism between the high-level symbols and the low-level network weights, it's really hard.
Why?
Because they represent knowledge so differently. Mapping between them isn't automatic. It often requires very careful, very clever handcrafting by the designers.
So humans have to manually figure out how the symbolic door concept relates to the specific pattern of pixels the network sees.
Pretty much. You have to design the schemas, the pathways, the rules for how these fundamental different computational styles communicate effectively. It's a major engineering bottleneck.
And I guess that difficulty is pushing people towards maybe hybrid systems that lean more heavily on deep learning but try to bolt on some symbolic structure.
Yeah, you see a lot of hybrid deep learning now, integrating deep learning with symbolic logic or maybe fuzzy logic, specifically trying to address things like symbol grounding or explainability in those big data models.
It really feels like this whole journey, these classifications, symbolic, connectionist, hybrid, it's like watching philosophy play out in code.
It really is. You can trace the lineage. Symbolic AI clearly comes from that rationalist tradition, formal logic going way back. Aristotle would probably get it.
Focus on systems of reason.
Right. Connectionist AI, well, that's rooted in empiricism, cognitive science, looking at how learning happens through experience.
And hybrid is the attempt to say, look, you actually need both.
You need the structure to define things clearly, and you need the flexible learning to handle the messy real world. The whole history of AI is kind of this tug-of-war between rules we write and patterns we observe.
Okay, this has been super helpful. So wrapping up, the key takeaways seem to be symbolic uses rules, but it's brittle, struggles with the symbol grounding.
Got it.
Connectionist uses network weights, learns from data, but it's opaque. The black box problem and can overfit or absorb bias.
Yeah.
And hybrid models try to combine them, which is probably necessary for more general intelligence. But engineering that combination, that bridge, is really, really tough.
That sums it up well. And for you listening, just knowing whether an AI system falls broadly into symbolic, connectionist, or hybrid tells you a huge amount immediately.
Right. It gives you a lens to understand its likely capabilities and its probable failure points, a critical filter. And thinking about that hybrid challenge, our sources really stress that getting these systems like CLARION to work requires this careful handcrafting. It makes you wonder.
What's that?
Well, it leaves us with a final thought, maybe a provocative question for you to chew on. If the human brain is arguably the ultimate hybrid system, smoothly blending innate structures and learned experience, does creating true general AI mean we need systems that are more meticulously designed, more architected with cognitive principles in mind?
Rather than just hoping intelligence will magically emerge if we just train bigger and bigger neural nets on more and more data.
Exactly. Is pure training enough, or does AI need more deliberate design?
That question, design versus data, is still right at the heart of AI research today. It's shaping where the field goes next.
It's a lot to think about. Well, that's all the time we have for this deep dive. Thanks so much for joining us.
Always a pleasure.
We'll catch you next time.